Astronomy Cast, episode 268 for Monday, June 4th, 2012. Energy. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville. Hey, Pamela, how you doing?
I'm doing well. How are you doing today, Fraser?
Doing really well. So once again, we are recording this episode of Astronomy Cast as a live Google Plus Hangout. We do this every Monday at noon. So if you ever want to see what Pamela and I look like, you can. And you can also, what's cool is we'll record the main show, and the people watching the show will give us their comments and questions and feedback and ideas. And then, but at the end, we'll stick around for about half an hour and just answer questions from people. So, you know, we sort of lost our question show of a few, maybe about a year and a half ago. Just
more than
so
that.
Busy. Yeah, because we're so busy. But we love the question show.
Yeah.
And so this is the way that we're feeding the question show back into the show. So if you want to come and watch that. And everything is all archived on YouTube as well, and you can access it all from, you know, if you go to our Astronomy Cast site, all of the episodes are available in full, the video on the pages with various episodes. So if just listening to us isn't enough and you want to improve the experience, then you can go and check it out lots of different places. So just want to let people know that they can do that. All right. Are you, shall we get cracking then? Do you have any more announcements?
I think the most important thing I can say is if you want to look with your eyes at images of the Apollo 15 landing site as seen by the Lunar Reconnaissance Orbiter, those images right now are in the Moon Mappers project at cosmoquest.org. So cosmoquest.org/mappers/moon. We're trying really hard to release some new science about this region of the moon that has actually had humans walking on it. And so we'd love it if you'd help us do science as well as learning science by listening to the show.
Yeah, we plan to turn you from passive listeners into active scientists.
Yes.
So this is the process. All right, well, let's get rolling. So our entire civilization depends on energy, getting it, converting it, burning it, and conserving it. But how do physicists think about energy? How do they measure and quantify it? And what is energy's special relationship with mass? Which is going to be the topic of next week's show.
Yes.
Because they're really one and the same.
They are, but you do deal with mass in a different different distinct way.
Yeah, absolutely.
I generally don't worry about the energy of my body. I do worry about what that scale says.
So I can remember, actually, I remember being in high school and learning about energy and how we think about different kinds of energy and how they convert from one to the other, how potential turns into kinetic. And it was actually a real revelation for me to see all that stuff and see how it converted from one form to another. So how do you sort of begin your explanation of energy when you bring that up?
Well, unfortunately, you do have to start with math. And the math for work and energy is force exerted over a distance on an object. And a force is how you change an object's velocity and how you change its direction of motion. So you have to be able to exert a force on an object and get that sucker to go somewhere in order for there to be work or energy that takes place.
So energy is measured of the output with time.
Yes.
Yeah.
Well, work over distance.
Work over distance. That's and so if you're going to raise an object up in, off the planet, you're going to be doing work on that object over the distance of what it's going to take to raise it. But then it's
force times distance equals work, just for all of you trying to keep track of things.
People love the math.
Yeah.
Yeah. Okay, and so then how is energy interchangeable? How are there different kinds of energy?
Well, it's a matter of this is one of those concepts that just hurts, and so I'm trying to figure out how to make it not hurt, and my brain froze for a moment because it just hurts.
Yep.
It's one of these things where, for instance, when you're walking along holding a weight, and it's your arms that are holding the weight, and you're moving forward. Well, your arms are just holding that weight in place, and so it's not moving relative to the force that your arms are exuding to keep that weight up. And so your arms aren't actually doing any work in the math sense that we just discussed. But then there's chemical reactions going on in your arms that are contracting those muscles that are causing the weight to get to stay up. And there's all sorts of chemical processes that are going on. And so when you look at the full chain of energy that went into this event, what you have is sun released light. Light hit plant. Plant took in light, had chemical reaction. Human ate plant, more chemical reactions occurred. Sugars or other forms of energy were carried to muscle. Muscle used this to do twitchy things that muscles do, that allowed you to hold up the mass that you're now carrying, and it's your body carrying it forward across a distance that is the work that you're doing.
And to even roll that back further, Big Bang happened.
Right.
Gravity sucked in all of the particles together to form the star. The compression of the star converted the hydrogen into heavier elements, releasing energy as radiation. It's energy, 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 energy. Each one is just this conversion from one thing to the other thing.
And you have to worry about all sorts of different energies in this, because you have down at the molecular level, you have the energy in the vibrations of the molecules, and so molecules can switch between different vibrational states. They're also rotating, so you have different rotational energies in the molecules. Then the atoms themselves have electrons that can be in a variety of different energy levels, and so you have all of these different atomic level energies that you have to track using quantum mechanics. Then when you have the chemical reactions going on, some chemical reactions pull energy from the environment. Those, when they occur, create a cold solution in your cup if you're doing a chemical reaction where you can see the frost forming on the reaction containing container. Then there's some reactions that they push energy out to the environment, and in this case you may see a flash of light, you may feel infrared radiation. That's warmth. When you feel warmth, that's infrared radiation that you're sensing through your skin. So you have that sort of chemical reaction going on, and it's also, you have to deal with collisions at all different scales. So you can have atoms colliding into each other, in which case the force of the impact can cause something to happen over the distance of the impact. And depending on how that interaction takes place, you can end up with things shooting off in different directions, things bonding together and flying together. So car wrecks and gas molecules colliding in the atmosphere have very, very similar physics, and it's all transfer of energy.
And I guess that's the key, is that transfer of energy. That energy turns from one thing into another thing. So,
yes.
So what exactly is going on when we say that energy is transferred? When we turn, say, potential into kinetic or kinetic into potential, what's actually going on?
Well, when you have potential energy, this is, for instance, trying to
lift a book up on the
I'm looking for something I can drop without causing pain. So I have a spool of thread right here. And right now, I'm exerting a force on it that is holding it above the surface of my desk. I'm not doing work on it because the sucker isn't moving. But I'm exerting a force on it that causes it to stay still. And potential energy is locked up in anything that requires a force to prevent that energy from escaping. So if I remove my hand, suddenly the potential energy that was tied up in the spool of thread that I was holding up, and those of you listening are just going to have to believe me, and as that object fell, it gained velocity because the force of gravity from the planet Earth was pulling the spool of thread towards the center of the planet. And then the energy from that fall, that kinetic energy, when it hit the table, created sound waves. So in that case, the energy from the fall got transferred to the table, caused vibrations in the table. The table, if I had high enough ability to measure thermal properties, I would have been able to see the table heated up. The air around it heated up from the sound waves going through it. Then that energy from the compression waves, that sound is compression of the air moving through the air, hit my ear. Energy was transferred to my eardrum that got translated into a neurological signal that my brain picked up on.
So much energy being dissipated from that from that drop. But I know that a certain amount of energy is always getting lost, right?
Yes. Well, so lost
Or
is the
not
wrong way
lost.
to. The
Yeah.
universe conserves energy.
Unusable. A certain amount of energy is getting lost to us.
Right, right. So within any given system that isn't perfectly sealed, and like the Earth is not perfectly sealed by a long shot, energy over time does end up going into places where we may not be able to access it. So Mars, I think, is the better example. Mars has an atmosphere that when sunlight hits it, it gets heated up, excited, and the collisions between the atoms in the atmosphere can periodically cause things to fly away. Now you add in high energy particles coming from the sun, they hit the atmospheric particles on Mars, and the energy contained in that molecule gets swept away from Mars. So Mars is slowly losing energy.
Right, but if you take, I mean, just for an example, right, if you take like a ball and you put it on the end of a rubber band and you stretch that ball down and you let go of it, the ball is going to bounce up and then it's going to bounce back down, but it's not going to bounce back up as high as it did.
Oh, you're getting it friction.
Time. Yeah, exactly. That there is a certain amount of energy that is lost through friction to heat.
To that system, yes.
And that system and that heat is then, the whole concept of heat is really that it's this energy that's being lost to us from that system.
Right.
And eventually, the whole universe is going to be heat, and it'll be all the same temperature and not usable. Like, these differences in heat that we can exploit. But that always sort of taught me, like, when you drop something and it doesn't bounce quite up as high as it did the time before, and you start out, it's potential energy at the top. You let go of it, it drops, it bounces. Right before it hits the ground, it's all kinetic energy. And then it converts back into potential energy as it rises back up, but each time it's less and less.
And the realities are that when we drop a real ball onto the table, energy gets lost to two major processes. One is when the ball hits the table, the act of compressing the ball, there's frictional forces in there. So when the ball uncompresses and springs back up, it's lost some energy, and it also loses energy to making sound. In order for a ball to bounce all the way back to where it started, it would have to be a soundless bounce. I mean, imagine a basketball game where you couldn't hear the ball bouncing, but the amount of force that you put to that first dribble causes it to always dribble the same amount. So you're basically walking around hovering your hand over the ball to give slight side-to-side forces to steer it, but that's all you'd have to do.
And I guess the point then is that the basketball player, as they are dribbling, is injecting energy back into the system. They're actually pushing the ball every time they hit it.
And that's the exhausting part of dribbling the ball, is you do have to just keep adding force, adding force, adding force. And otherwise, it's not going to make it back up to your hand the next time.
So then how do physicists measure energy?
It depends on the system we're looking at. We don't like to do things just one way. That's one of the hard things about science is energy's everywhere. There's lots of different ways to deal with it. So we look at energy in terms of what is the temperature of something, because that speaks to the kinetic energy that's in the motions of the particle. We look at how much mass is there, because, well, the mass that's tied in, that holds its own energy in its ability to, a neutron can decay and release energy. Lots and lots of particles actually can decay and release energy, and if you get fission and fusion going on, depending on where you are on the atomic table, that's another way to release energy from mass. So then we also start looking at, okay, what are the forces that are acting on something that is causing it to have potential energy locked up in the system as well. In general, what we're looking at can pretty much always be broken down into the activation energy available for molecular reactions, the nuclear energies that are tied up in potential decay processes, the kinetic energy in the system, which is from all the different varieties of motions, and the potential energies from any other external forces that are acting on the system.
Now, what about the sort of gaining and releasing of energy? So, is there some way to measure how fast things are getting rid of energy? Is there a limit to how fast something can get rid of energy or gain energy? Or
Well, the limit really has to do with the ability of the surrounding materials to transfer that energy. So, for instance, if you have a copper box and you put a piece of dry ice into that copper box, I don't know why you would do this, but we're going to pretend for a moment. So say you have a copper box and you stick a piece of dry ice into it and you leave it out in perfect darkness but in a 100-degree oven. Well, very quickly, the dry ice is going to melt and try and explode your box because the dry ice gas is bigger than the solid dry ice and it's trying to take up space inside the box. Now, if you instead of having copper, which transfers heat very readily and allows the heat from the outside, heat is a form of energy, to go inside and use that energy to change the state, in this case, of the carbon dioxide. If instead of having copper, which facilitates that transfer of energy, you have something like styrofoam that doesn't want to allow energy to transfer, then the ability of the energy to flow from that hot oven to that cold dry ice and facilitate that state change, the energy can't flow. So that is a slowing down effect. You also have to look at how effective is a particular molecular transfer. Is it something that readily changes? Is it something that you need a lot of energy to encourage the change? So there's rates involved that change with temperature as well. So melting ice, the ice is going to melt faster if you're on a copper substance at a much higher temperature that's readily transferring in the energy than if you're on styrofoam at a 35-degree temperature, 35 degrees Fahrenheit, just a couple of degrees centigrade.
So, and I'm going to ask you, one of those 4-year-old questions, which is, where did all of the energy come from? What was like right at the Big Bang, and we've got all this energy in the system, sort of what was sort of the earliest states of it before, leading up to what we have today?
We can't say where all the energy came from.
No,
if we could do that, I could tell you where the universe came from.
No, I understand that, but I'm talking about the actual, right after the Big Bang, when all of the energy of the entire universe was injected, was there.
So initially, everything was in the form of light energy. Everything was basically photons. And then the color of the photons, which is a measure of the energy. So red is lower energy than blue, which is lower energy than X-ray, which is lower energy from gamma ray, and all the really high stuff we just refer to as gamma rays. So when the universe first formed, everything was light, and I actually love the poetry of our universe started as pure light, and then the mass separated from the light as the universe expanded and cooled, and it hit the temperature where suddenly the light was allowed to solidify out into mass. Mass is just solid light.
Yeah, and I was going to get into that conversation. So for a while there, all the energy in the universe was essentially just super high energy gamma radiation?
Pretty much.
That was it? That was the only kind of energy there was in the whole universe?
Yeah, kind of sad.
And yet...
Well, there was actually a point where even light, the forces hadn't even split if you go back far enough. So you go back far enough and it was just stuff we can't really speak about in a sensible way. Not even the forces had separated.
Right.
So without electromagnetism by itself, you can't really say the universe was pure light. But that split up so quickly, we're going to ignore those fractions of a second.
Right, okay. But then let's compare and contrast that to the far, far future of the universe. Right.
So the far, far future, the kind of neat thing is what was once pure light will, assuming protons decay, again be pure light. So what we have is a far distant future, again, assuming protons decay. We don't know if they do. We actually have limited to they seem to be stable for at least 10 to the 34 years, which is a lot of years. So assuming that they actually do decay, then eventually all of the black holes will have time to evaporate. Even the big suckers will eventually start evaporating once they no longer have cosmic microwave background energy to suck in. So as the black holes all decay and the particles themselves start to decay, we'll end up with diffuse energy everywhere. And in this case, it's not a matter that the energy that it's too hot and too dense to form mass. It's a matter that the mass has had time to turn back into pure energy, and the energy is spread out so much that there isn't enough in a small enough space to form a particle again.
And so you would end up with the whole universe being very long, assuming, I guess, dark energy is still acting and still accelerating the expansion of the universe. You would end up with a whole universe that is rapidly expanding, I guess, wavelength stretching radio waves at the very low end of the electromagnetic spectrum, or I guess you would end up with photons of light that could have a wavelength that could be light years across.
Eventually, if you expand the universe long enough, that's just a matter of letting your clock run out.
Yeah, in a clock that will never run out.
Well, and I mean, that's the other thing we don't know, is when you start talking about the end of the universe, for all we know, we're eventually going to merge with another universe. So there's a lot of what-ifs involved in the ending of things. But in the beginning, I feel safe in saying that at the beginning, it was originally so dense, so hot, that even all the forces were the same sucker. Over time, universe cooled, forces split out, everything became pure energy. Over time, universe cooled, got lower in density, and mass was able to start forming. And then eventually we even reached the point where neutral atoms were able to start forming. And that happened about 300,000 years after the Big Bang.
So where do the, and I think we probably need to do a whole show on the laws of thermodynamics if we haven't already. Where do these play into this concept of energy?
Well, I mean, zero is two thermometers that read the same temperature experiencing the same thing. That's just a matter of making the science so that you can communicate from one person to another. The idea that heat travels from high energy heat to cold energy, that's a matter of everything basically equaling out. So you can imagine the gravitational way of thinking of this in terms of if you have a flat surface and you have a cup of water and you suddenly remove the walls from the cup, the water is going to spread out so that it has an equal potential everywhere. Well, energy in the same way, if you have a hot room and a cold room, subtract the wall, the energy from the hot room is going to equilibrate between the two rooms. So cold is a lack of energy, and so the energy will spread out so that it's equal everywhere.
And I mean, I know there's more laws of
there's more laws, but then you
yeah.
start getting into things like entropy and stuff like that. So
right, but in this case, yeah, I mean, entropy definitely, that's a whole show on its own as well, actually. But this whole concept of equilibrium, that the fact that the energy is looking to balance itself out between different situations, that balls are looking to roll downhill, that ice cubes are going to melt, that rubber bands want to be, snap back together, that it's always looking for this equilibrium, and this is what. Oh, go ahead.
And things are always trying to get down to the lowest allowed energy state as well. So you don't have a room where suddenly all the energy in the room goes to making a certain number of the atoms at the highest possible energy level they can be at. Things are going to try to equalize out to the lowest possible energy across the population. And it's the population stuff that starts to really look interesting.
What do you mean by that?
So again, we can look at Mars' atmosphere as a great example. You have a whole bunch of different types of atoms in all of our atmospheres. So here on Earth, we have oxygen, we have nitrogen, we have carbon dioxide, carbon monoxide, all the other nasty pollutants out there. And each of these different molecules and atoms has their own mass. Now they're trying to equalize to spread out energies that are equilibrated between the different populations. And this means that the heavier mass molecules are going to be moving slower than the lighter weight molecules as they spread out the energies across all the populations. Now, you're always going to have a few things that are moving a lot faster and a few things that are a lot slower, but there's this bell curve distribution of velocities, and the height of that bell curve is going to depend on the mass of the things that you're looking at.
Is there a way, is there like a minimum measurement for energy? I know that for example, there's like a Planck length version of measuring energy.
The idea for minimum energy is the idea of absolute zero. This is when you take an atom and you remove all energy from it such that the electron's not moving, all vibrations have stopped. It's frozen. But we can't get there. There seems to be Bose-Einstein condensates are as cool as we've gotten, and there seems to always be some minimal amount of vibration in the system, some quantum noise.
And so we can try to get closer to that
we can try and get
zero,
closer.
But it is theoretically impossible to actually reach it, or practically impossible to actually reach it.
It's practically, and here the issue comes to be, how do you perfectly isolate something to remove all the energy of it, when the reality is that energy always wants to flow down to that lowest energy state and equalize everything out. And so we do all sorts of crazy manipulations of magnetic and electromagnetic fields, of magnetic and electric fields rather. We remove all other molecules so that you don't get any collisional excitations. We do everything we can to stop that motion, but at the end of the day, the universe wants to equalize everything. And in fact, our own planet Earth is constantly radiating away energy that's trapped in the planet as we try to freeze out to equalize with the universe around us.
That is really cool. All right, well, I think we're running out of time for this week, but I know the next week we're going to actually connect the dots. So we're going to talk about how mass is actually, as you said, frozen light, and we'll talk about a bit about how those discoveries are made, and then just how mass works out, and talk a bit about the new discoveries that have been made about the Higgs boson, although that's probably a separate
show. And we'll
show.
bring in things like how radioactive decay keeps the Earth warmer than the sun alone can do, and things like that.
And what's between mass and weight. So.
Yes, yeah, that one confuses everyone.
Yeah, absolutely. Great. Well, thank you very much, Pamela, and we will talk to you next week.
My pleasure. And now everyone has seen my brain stop for 5 seconds.
Yikes! Her brain just stopped for 5 seconds.
Okay, saving and quitting.
And by next week, we might mean again this week. So
yeah, that's true.
We both have time. Pamela's not traveling much. We will get these episodes out the door. So it's nice to be recording an episode in the same month that we're actually existing. So that feels really good.
Yes.
Someone on YouTube, I think, mentioned that. They're like, the 4th? What? The June 4th? Yeah, June 4th. This is the episode for June 4th, which is 3 weeks ago. So yeah. Sorry.
No,
okay.
There will be some episodes missing here and there in July because my travel does come back up to attack, but we'll try to either pre-record or we'll go back to what we're doing right now and record Mondays and probably either Wednesdays or Fridays.
Atomic NY asks, what about dark matter? Is that a misnomer or is that actually a form of energy?
Well...
I guess, I mean, dark matter isn't a form of energy.
No.
Unless
dark matter. Well, dark matter.
Unless it's frozen
mass.
Dark matter, but unless it's frozen dark energy, right?
No, we're not going to go there.
No.
You are introducing misconceptions.
No. I know.
No.
All right.
So dark matter is stuff. It's simply a form of mass that doesn't interact via the electromagnetic force, as near as we can tell. Dark energy is confusing because it's either some sort of a force, some sort of a pressure, or simply energy that permeates all of space. And these three things are all different ways of looking at the same effect.
Right.
Whatever
is dark
it is,
energy,
it's pushing us apart.
Right. So is dark energy a form of energy? Yes.
I wouldn't say dark energy itself is a form of energy, but it may be capable of exerting energy. So gravity is not energy. But when I drop my thread, it falls because gravity is a force working over a distance. So dark energy could be a force working on stuff over a distance, thus adding energy to the system.
Right, but I guess the issue being the fact that it balances out to zero, doesn't it? I mean, the amount of energy that is pushing apart the universe is going to be balanced by the gravity, the additional potential energy for the gravity that is being introduced at the same time. That's going to, I guess it's not, is it? No.
No. This is one of those things that totally mucks folks up, is dark energy is a scalar, which means it doesn't care what direction you're coming from, basically. And it seems to be constant over time, which means that as the universe gets bigger, the total amount of dark energy in the universe is also getting bigger. So this sort of defies the whole closed system idea, because
Right.
there's this weird field everywhere that's pushing.
Yikes. So,
Yeah.
but the point being that I guess it's, but then would it be, so if you're moving two objects further apart that would be gravitationally bound to each other, are you almost siphoning away some of their potential energy? That normally they would be attracting each other, but now because you're pushing them further apart, they're going to have less potential energy to pull themselves together again.
There it's all conserved. That's a conserved system.
Okay, so Robin Clark asks, since everything is moving, the Earth is rotating, the galaxy is moving through space, and so on, does anything really only have potential energy? So I guess this is kinetic energy.
Well,
right?
it depends on your frame of reference. You can define a frame of reference where, because within that system, the way you've defined it, you have a closed system, and all the velocities add up to zero within that system. You can have a closed system with a defined frame of reference that is, as long as it's an inertial system, you only have potential energy.
Yeah.
So I can define the thread sitting on my hand as being a closed system that only has potential energy.
Right, and not include or specifically reject the wavelengths of light that are striking it from your light bulb, and the sound that's hitting it from your talking, and the particle decay and the potential protons that are going to be decaying inside of it over.
Okay, so
yeah.
Yes, I was overly simplifying.
No, but that's the whole point, right? The point is that if you look at anything, you've got to make it a closed system.
Yeah. Yeah, you have to remove the light, you have to remove the colliding particles, or have them collide such that it sums to zero.
Yeah.
As long as everything sums to zero, that's what matters.
John McKinney asks, I think I heard that one aspect of the accelerating expansion, combined with the assumption that protons can in fact decay over long periods of time, will result in the conversion of all the mass in the universe to pure energy a very long time from now. So this is what we talked about, the fact that in theory every proton will decay over the course of 10 to the power of 34, 37.
More than that. We've put a limit on it.
Whatever, 10 to 50. A big number. 10 to the power of 50. A 1 with 50 zeros after it.
I love the fact that you're just making up numbers that people spend their entire careers trying to define.
They haven't seen a single proton decay yet. So
no, so we know a greater than 10 to the 34
exactly,
years.
Which is why I am free to make up numbers bigger than 10 to the power of 1 followed by 34 zeros.
Yes.
But that's this idea, right? And then we'll get these protons decaying, they'll all turn into energy, and dark energy will be stretching the space, and you'll end up with just wavelengths of light. We did a whole episode on this, two-parter.
Yes, we did.
On
how the universe will end.
How the universe will end.
We did how the Earth will end and how the universe will end.
Yeah, we how the solar system will end.
Right.
We talked about humanity, life, the Earth, the solar system, the sun, the solar system, the Milky Way, the black holes.
Yeah.
Energy. Everything.
Energy death is the end of everything.
Yeah.
It will all end in ice, not fire. Dark energy got rid of the fire option.
So Mr. Arif says, come on, show us some image in space using any live space viewer. So that's what we do on Sunday nights. So if you actually look back in the Universe Today YouTube feed, you'll see last night we put a whole bunch of telescopes connected to space live, which is every Sunday night.
And if you sign up for the CosmoQuest newsletter by signing up for an account, you will find out ahead of time when all of these things are going to happen.
Let's see if we have another question here. This is a question from Maxim Levin, completely unrelated to energy. How do astronomers measure sideways motions of nearby galaxies?
We don't. So we can only measure velocities of galaxies relative to us. Now what we can do is we can infer other motions, but we can't actually measure it.
And so that's done. Right, but like we can measure stars moving sideways based on the parallax.
Parallax, it measures distance. What we do is we look at what is called proper motion.
The proper motion, yeah.
So with stars, they're close enough that you can actually see them chugging across the sky if you look for enough decades, centuries in a few cases. So by looking back at glass plates and very carefully measuring, Barnard star is a great example, measuring the motion of stars relative to background galaxies, relative to the most distant stars that we're able to see, we can see stars moving through the sky. Then we use the Doppler shifting of light, which tells us how things are moving forward and backward relative to us, and so we can get the two motions. With galaxies, they're so far away that we can't measure any motion in the plane of the sky. We can only measure perpendicular to the plane of the sky. This is the Doppler shifting forward and backward motion again. Now if you have a cluster of galaxies, you can make estimates of the mass, you can measure the Doppler shifting relative to the center of mass of that system, and so you can infer orbital motions.
Right. Maxim Levin asks, will the protons be ripped apart by dark energy as well? And this is, I guess this is this big rip.
Right. So as far as we know, the amount of energy in dark energy is fairly consistent with the amount of energy in a few protons per cubic meter. This isn't sufficient amounts of energy spread out over that cubic meter to tear apart individual particles. The particles are held together via their own force. So it's via other forces that you look at decay, and then the energy from the decay will spread out evenly across space.
Right, and this is one of the big questions that physicists were looking to explore just a couple of years ago. Yeah. The idea is dark energy a consistent injection of energy into the universe, or is it increasing over time, or is it decreasing over time? And so if it's increasing over time, then you can imagine the amount of actual energy that's coming into the universe is going to be increasing and increasing, and so what effect it has on what it'll be separating will start to grow. So right now, for example, galaxy clusters are pulled apart, but maybe in the future individual galaxies might get torn apart, and then eventually solar systems, and then eventually individual atoms if this dark energy. But this appears to be not the case.
Right.
Yes.
So as far as we know, the amount of dark energy per cubic meter is constant within the limits of our measurements with time, and this means that things that are held together via electromagnetic forces, strong and weak forces, chemical, which ties in with the electromagnetic, but when you start thinking of things that are chemically bound together like compressed wood and desks and stuff like that, all those sorts of things, the forces that are holding them together is a lot stronger than dark energy. So our bodies, our tables, our solar system, our galaxy, all of those things are going to stay gravitationally, chemically, and otherwise bound together within an expanding scenery, I guess.
Yeah. Cool. I've actually got to run.
Okay.
My sister is going back home, so I'm going to go say goodbye. So I better wrap this up. But it was wonderful to talk to you again, Pamela. I'm really glad that everyone got a chance to watch us. This is going to be available on the Astronomy Cast site, so if you want to watch this after the fact, you can watch it there, or on CosmoQuest, or on the Universe Today YouTube channel. And remember, we're going to try and record another episode this week, maybe. Yep. Mass. Try and get even closer to now, so that'll be great. So thanks to everybody who's watching, and we will see you all next time.
Sounds great, Fraser.
Bye, Pamela.
See you later. Bye-bye.